Okay, so continuing with 5.4, I will recommend you use a really sharp pencil or another piece of paper or just write really small for this example. All right, I'm going to do part C. So we're going to have to analyze the second derivative. So let's find the first derivative so we can keep going. So we have ho d high minus high d ho all over ho ho, x squared minus 4 quantity squared. All right, we should probably simplify before we keep going too far. So we get 2x cubed minus 8x minus 2x cubed minus 2x. And keep in mind this is all over, just trying to save some space here, x squared minus 4 quantity squared. All right, so simplifying the numerator, we get negative 10 x over x squared minus 4 quantity squared. So this is our first derivative. Or we can use this to now find our second derivative. All right, so we have ho d high minus high d ho. Be careful with this one because you have to use the chain rule. X squared minus 4 times the derivative of the inside. Okay, all over, come on. All right, all over ho ho, which this time will be x squared minus 4 to the 4th power. Okay, so we could do a little bit of simplifying here. All right, I'm going to start off by factoring out common terms. So I get negative 10 x squared minus 4. That can come out of both of these. All right, and so we write what's left over. We'd have an x squared minus 4 left over. Now be very careful with the signs. I took out a negative 10, but I still have this minus in the front. So it's going to be minus a 4x squared. Okay, everything else we've taken out. All over x squared minus 4, quantity to the 4th. All right, x squared minus 4x squared. All right, gives us, let me scoot this over. There we go, negative 10. That gives us negative 3x squared minus 4 on the inside. And notice I didn't rewrite the x squared minus 4. That's because I canceled it out with one of the factors in the denominator. Alright, so I would rather not be negative up here. I'm not a negative person, right? I'm always positive. So I'm going to factor a negative out of here. So it just changes the signs and cancel that out. Alright, so it'll make it a little bit easier for me to analyze this function. Alright, so the only places that our second derivative is undefined would be at our vertical asymptotes. Okay, negative 2 and 2. On the other hand, if we look at our numerator, where is g double prime of x equal to 0? Well, this part's always going to be positive, so it's not equal to 0. So we have no possible inflection values. All right, but that doesn't mean that we can't be concave up, concave down, whatever. All right, so we'll analyze our function, our second derivative. So we have negative 2 and 2. Let's see, let's change the color here so it stands out a little more. Pick some numbers in between. Plug them in. All right, if we plug in 0 in the top, we're going to get a positive number. If we plug in 0 in the bottom, we're going to get a negative number. Okay, so with 3, positive on the top, positive on the bottom. With negative 3, positive on the top, positive on the bottom. All right, so our function is concave. Actually, we should say g, but g is concave up like a cup. Anywhere negative infinity all the way up to negative 2, or from 2 to infinity. And our function's concave down like a frown in between those vertical asymptotes from negative 2 to 2. All right, so don't forget when your second derivative is positive, it's concave up like a cup. And when it's negative, it's concave down like a frown. There are a couple more. We'll do a few of these. I'm not sure how many we'll get to because they require quite a bit of algebra. All right, but we're good at that, so it doesn't matter. So the first derivative is 4x cubed minus 12x squared. We're not analyzing the first derivative right now. We're focusing on the second one, so we'll keep going. The second derivative is 12x squared minus 24x. That's not going to be undefined anywhere, so we just need to determine where it's 0. If we could factor out some things. So we have possible inflection values at x equals 0 or x equals 2. So we need to analyze those on our sign chart. Okay, x and f double prime. We have 0 and 2. Pick some numbers in between. Alright, so maybe 1, 3, and negative 1. Plug those in. If we plug in 1, we get a positive and negative value. That's a negative. Okay, positive, positive for 3. And we get negative, negative for negative 1. So there we go. And if you were being technical about this, you want to write this out specifically. Alright, well, we had to determine the concave up part. It's concave up from negative infinity to negative 1, and also from 3 to infinity. It's concave down, like a frown, in between there. Alright, and it has inflection values because these are changing signs here. Alright, F has an inflection point at x equals 0, since the second derivative changes from negative or positive, from positive to negative at x equals 0. Similarly, F has an inflection point at x equals 2, since f double prime changes from negative to positive. At x equals 2. There we go. Alright, so it seems like quite a bit of writing, but it's important that you emphasize what function you're talking about and why these things are happening. It'll help you pull this together. So E is another one that'll just take quite a bit of time. Alright, so I'm going to skip around. I think you have the basic idea. We can always go over that one in class. G, this one's not going to be too tough. But I think we can do that again in class, because x to the 4th, you should know, just looks something like this. It's not going to have an inflection point. It's going to be concave up for all these parts. Alright, but the last two are pretty neat because it helps if you know what the graph looks like. Alright, so we know, or you should know, x to the 1/3 power, the cube root of x, looks like this. So you should know that it would be concave up from negative infinity to 0 and concave down from 0 to infinity. And also there's an inflection point at x equals 0 since f goes from concave up to concave down. Alright, you could also do that with this function here. So the first part would be like this. Okay, and the second part would be like this. And it is continuous because they're both 0 there. So it is concave down from negative infinity to 0, and it's concave up from 0 to infinity. Alright, so again, there would be an inflection point at x equals 0 because the second derivative changes signs there. Alright, so we're probably just going to do one more and save that last page for another day. Alright, we have the second derivative test. Remember, we had the first derivative test. It tells us if it changes from positive to negative, it's a maximum, a relative maximum. If it changes from negative to positive, it's a relative minimum. We're going to be able to test for relative extrema using the second derivative. Alright, so if it's a critical value, if the second derivative exists around there, alright, if the second derivative is positive, then it's a relative minimum. And if you think about it, it's concave up if it's positive, so there'd be a minimum there. Alright. Also, if it's negative, there's going to be a relative maximum there. Alright. And then if it's 0, then the test fails. Oh no, and we have to use the first derivative test, okay? But no big deal, we can do this. Find the coordinates of the relative extrema. So we're going to try to do it using the second derivative test. So first find the first derivative, negative 15x to the fourth plus 15x squared. Remember, we're going to find our critical value, so if we factor out this, we would get x squared minus 1. So we have possible critical values at x equals 0, x equals negative 1, x equals 1. Alright, so find our second derivative here. It's easier probably to use this form rather than this one. Alright, negative 60x to the third plus 30x. Alright, so here we can just analyze, test the different values, alright? If we plug in 0, we get 0. So that means we have to use the first derivative test. Alright, if you plug in, let's plug in negative 1. So that's going to be here, negative 1 to the cubed is negative 1, so that'll be 60 minus 30. So that'll be a positive value, which means that we have a relative minimum value at x equals negative 1, since the second derivative is positive there, and because it was a critical value. Let's see, if we check B1, plug that in, we get negative 60 plus 30, so we get negative 30. So that means there's a relative maximum value, max, at x equals 1. Alright, and that's because f double prime is negative there. Now we have to double check 0. Alright, we're going to use our first derivative test. So 0, maybe like 1/2, negative 1/2. Oops, there are x values on the top, and the first derivative, plugging these in, this part will be negative, okay, because we'll get 1/4 minus 1. This part will be negative. Plug in 1/2, same thing, we're going to get negative. So there is no extrema, we could say that way, at x equals 0. Alright, so that'll be good enough for today. Keep working on your worksheets, and we'll finish the rest on the next video.